So I understand my slides are visible. Please mute your microphone. Yeah. So today we will discuss uh, a new topic that is on dimensionality reduction, and we particularly see what does this task means and its importance in designing or in importance in machine learning in general. So this is the reference where you will get most of the topics covered by this under this. So first, that motivation, what I was mentioning, that why you should reduce the dimension of a feature vector. So dimension here refers to the dimension of the feature vector, uh, which is the which is basically dimension of the data point from the machine learning jargon. If you reduce dimension, definitely your these are certain advantages. So which means that if you can reduce dimension without losing the information content. So that is the condition. Then you have advantages because it would reduce the complexity of inference, memory, and computations because of just sheer the size of the data becomes smaller. Not only that, other issues are there when you are just representing sufficiently. The information is sufficiently represented by that set of no, by that kind of, it's a kind of minimal requirement of representing the information with that kind of dimensional space. So that itself removes a lot of redundancy of the data and improves the makes your design efficient or learning task easier uh, with respect if you have the data in that way. So as we said that the complexity depends on the number of input dimensions and basically the size of the dimension and also the size of the data sample. So number of input dimensions means here each dimension could be considered as an attribute, as I mentioned earlier also. So you are reducing the number of attributes, and because many of the attributes are very much correlated, so one of them could be sufficient and others could be ignored. So in that way, it reduces the complexity. It saves the cost of extraction of features if you are extracting only the set of attributes which are going to be used uh, for your classification task or learning task. And because of the smaller dimension, the models would be also simple. And particularly in small data sets, these are more robust. So explainability will be better with fewer features. Also, as you can see that the in a lower dimensional space, they are convenient for visualizations, for plotting, etc. So there are two major approaches which we'll be uh, discussing under this particular task. One approach is feature selection. That means you have a set of features and you will be selecting a subset of it which are sufficient to represent the information what is there what is there in the data points or data distribution. So the problem would be the selection of suitable subset, which means if you have d-dimensional data, to find k which is k is less than d, that would k number of dimensions or attributes and discarding the others. So simple selections or subset selection method. Whereas feature extraction, it just directly does not do that kind of selection. What it does, it makes a combination of existing all the dimensions, some subset of dimensions, and uh, basically it's a projection. So feature extraction is a kind of projection of your higher dimensional space to a lower dimensional space. Projections here in the sense of selection also could be considered as a projections, but that is just you can say orthographic projections on a smaller dimension space. But feature extraction is projection could be any arbitrary linear combinations of certain subsets. So a new set of k dimensions that are combination of original d dimensions. It could be linear, it could be nonlinear also. And there are methods which are which we'll see that which can be categorized as supervised and unsupervised techniques, which means that your feature extraction may be guided by supervised levels, supervised data set. That means levels are given, and with respect to that, because you know the class distribution, so with respect to class distributions, you are designing the feature extraction computation in such a way that it becomes efficient, or it reflects that distinctions between classes. Whereas unsupervised techniques, you do not have any kind of class labeling, any kind of labels on the data. That means the class distribution is not given to you. It is just data distribution on the data space. And from there itself, you are trying to find out, that the required dimension or required subspace which is sufficient to represent that distribution itself. So it's a kind of because it does not use any label, and you do not it is not also given to you. So these techniques are called unsupervised with respect to this task, this dimension reduction task. So we'll discuss two such methods. PCA, that principal component analysis, it is basically an unsupervised technique. Whereas someone's microphone is on, please mute it. And the other method, that is LDA, or linear discriminant analysis, that also we'll discuss. Fisher's linear discriminant analysis, that method will be discussing here, and they are actually use the class levels. So we'll see that. So we call it supervised technique for dimension reduction. So both are a projection of features vectors to a lower dimensional space. But as I mentioned, that in the first, that is in the PCA, it is the data distributions which you are capturing. Whereas in LDA, it is a class distribution which you are trying. That means the separation of classes after the projections should be should be kept in order, should be preserved. So that is the objective there. So let us start with these feature selection methods, and I'll be discussing two very straightforward and simple methods. They are subset selection methods. So in this case, basically you are trying to select that subset of features which are giving good performance with respect to. So these are supervised techniques. These are supervised methods. That means you have already a labeled data set, and so you can perform a classification task of classifications, or you can train a classifier and check the performance using the feature sets. Now you can given this task, so your objective is to select that subset which is giving the best performance, right? Which is giving the best performance. So in that way you can formulate this problem. So as a performance measure, let us in an abstract way, let us represent it as an error in validation set. If the features set F is used as input, that means F is the set of input features with dimension D. So as you can see that with a subset, this dimension will vary. Now you can consider any kind of classification method, like decision. So far, whatever you have learned, and later on also you'll be learning. So any one of these methods can be used for this designing of this classifier and judging the performance, evaluating the performance thereafter. And but in our subset selection method, overall approach, we'll be considering greedy methods. As you see that this is a combinatorially explosive problem. If we consider every possible subsets And if there are total number of dimension is d, so there should be 2 to the power d subsets, as you see. So for every possible subset, you may you may design the classifier with respect to that subset, with respect to that input data, and you can always find out what is the performance on a validation set. And then you can choose that subset which gives you the best performance or the minimum error in this case. But naturally, this is combinatorially explosive, and like any kind of methods, this can be shown also. It's a subset selection is also an NP-hard problem or NP-complete problem. So in this case, we'll be again using heuristics, and a greedy heuristics we'll be using. So there are two methods which are almost same. Only thing is that in one case you build up feature sets starting from the null. So actually you can start with a single feature. So you consider the feature, you can consider all. So you are basically building up from the null set to a required subset, which is giving the optimal performance. Optimal in the sense, the locally optimal performance with respect to your search. But no, the other method would be that you start with the full set and then you go on reducing till your performance is improving. So in both the method is something like that. So you start with in the forward selection method, you start with a small set, which is minimally 1, and go on adding features till it stops improving the performance. Similarly, the other was backward selection method. So these are one is sequential forward selection and sequential backward selection, because one by one, in the first method, one by one, you are adding one of the dimensions or one of the attributes to your set. And since it is greedy, so you can always understand that, which means you can have the possible candidates at that stage for addition, and you should choose only that candidate which gives you the best performance at that stage, and you go on doing these things till it improves, till it stops improvement. Similarly, for the backward selection also, as I mentioned to you, you start with the full set of features, and one by one you delete till it stops it. So in the sequential forward selection method, the algorithm steps are like this. I have already described. I think it would be quite easy to understand that. Say, as I mentioned, you start with the null set and you select the corresponding attribute. So xi here represents the attribute here, not the data point. Xi here represents the attribute. So ith attribute. So which provides least error, right? So if there are d dimensions, that means there are d such attributes, and you select that attribute which provides the least error. So you can update your f and repeat above 2 steps till no more addition is possible. So you just go on doing these things till no more addition is possible. So it's a local search method, as you see, does not guarantee optimal feature combination. And the cost of training and testing is of order d squared, because there are d features. So for every feature dimension, you are going to first for every feature you are testing it, and you are doing it for all the d features, right? So order is d squared. So every loop it will be of order d, and overall the number of loops will be also of order d. So that's how it becomes order d squared. And sequential backward selection, it's just the complementary method. You start with the set of all the features, and you have to reduce that feature, delete that feature which selects xi which provides least. No, actually remove xi if yeah, actually which provides not least, which provides the maximum error, which provides the most error in this case, because you are removing it. So please note this correction here. It should be highest error. Right? Most or highest, rather the largest error. And then you can remove it. So if it is naturally, sorry. Oh, no. It's all right. I think it is all right. The description is like this only. It is giving the error after removing, this is error, and so this error should be list. After removing, this error should be list. I think this is okay. Sorry, this is okay. And then if the error is less, then you are going right. Yeah, I think. Yeah, so the description is fine. So this is also local search method, and it does not guarantee optimal feature combination. The cost of training and testing also is here, order described in the same way. But as you see that this method is a bit, in absolute sense, it is more computationally intensive than the previous one, because you have started with more number of features. When designing a classifier, you are using more number of features for testing at the second stage itself. Second step, your dimension, you are using the larger dimensions in these steps. So that's why it, in absolute sense, it is computationally costly. Otherwise, order-wise, they are same. So any questions? Any question on the algorithms which I just discussed about the feature selection? Okay, so let me proceed with this particular discussion. So now I will be considering the methods under this feature extraction. And as I mentioned, there are two methods that I will be discussing here. One of them is principal component analysis. And the problem statement here is that you have to map your d-dimensional input or input space to a new k-dimensional space. So with minimum loss of information. Now, this is a kind of motivation. So you have to understand that how do you measure information here? How do you consider the mapping? What is meant by mapping? What is meant by information? Now, there are various ways you can measure information, as we know. Like one good way is that very directly, I mean, you know that entropy measure. Entropy measure is the measure of information. The other thing could be a measure of information is a variance. So if you relate, so if you consider a a particular data set, and if you consider a transform data set, now if you find the variances, this total variance of the data set that is more or less intact, so the transformation is also transformation is also keeping the information. Now in that transformation, if your reduction, if the dimension reduction happens, and still you find that the variance is mostly preserved, so it's a kind of trade-off. So you can explain, because in a linear transformation you can prove that actually these variances of the transform space cannot be more than the total variance of the data. So it should be always less than that. And so you require that kind of transformation, which would which would be preserving the variance, or which would mostly preserve the variance, which means the variance of the transform space would be as close as possible to the original variance. So if you are having this kind of scenario, so that gives a measure. That gives a measure of your loss of information. That means if your variance reduces, which means certain part of information gets lost. So that is the kind of, I should say, layman's way of understanding this metric variance with respect to this information loss. So, but we'll be using that very simple concept. So what we will do, you have the d-dimensional data. So can you project this data uh, on a particular along particular direction? So you just convert it into a one-dimensional data, which means, so if you have a d-dimensional data, project along any particular direction. This is a linear transformation, right? Projections, you are just using dot product along that directions of that data. So the data point what you get in that projected data, so you compute its variance, right? Now this variance would be naturally would be much less than the total variance of the data. But the question is that which direction will give you the maximum variance? Can you find out the direction which will give you the maximum variance? So, for example, just figuratively, if I draw something like this, say you have two-dimensional, say, data points, right? So you have two-dimensional data points like this, some distributions, and I consider certain directions, and then I'll be projecting it. I'll be projecting this data along these directions. Projection means, that you take, in this case, diagrammatically as if you are taking perpendicular intercepts, and depending upon certain coordinate system, say this is your vector representation, these are directions passing through that center. Usually, this passes through the mean of the data point, okay? And then these intercepts now represents the data points. So you are measuring these lengths. These are actually the one-dimensional data points. And then you can compute its variance. So you compute its variance means it's spread across its mean, and that would give you the variance. So which direction? So there are so many possible directions are there. Along which directions the variance would be maximum. So you consider that is the principal direction in that sense, right? That is the principal directions, and the projected component is the principal component. So, in this way, you are basically finding out. So that is for the first component. Similarly, you carry on this process on the on the other directions also, which means what you do, you exclude this component, and that means you consider the orthogonal directions along all other orthogonal directions of the given the first principal directions. You find out that where you get the maximum variance of the projection of the maximum variance of the residual data point. So you know that I consider a data point is a residual data point. Suppose I have a data point represented by a vector. See, all are vectors. Huh? There is a coordinate conventions, and I have a directions. Say this is my directions along which I got a component. So this is my component. So the residual component along this direction is this one, right? So this is my residual component. Now, if you have a d-dimensional subspace, so d-dimensional space, so one of the dimensions, say this gives you the one of the dimensions, and then there would be d minus one dimensional, axis, orthogonal possible axis, along which so you just simply deduct this particular component from this vector. That would be your residual. So along which there would be so many orthogonal directions along this, right? I'm considering the higher than 2. Of course, in 2 dimension you have only one orthogonal directions, but in higher dimensions you have, like in 3 dimensions, you have many orthogonal directions, right? So on the plane, whatever directions that is orthogonal direction. So in which directions, out of them, along which directions you get the maximum variance of the residuals, and you go on doing these things. So each one will give you a component. Each one will give you a component, and you keep the measure, you keep the residuals, and then you consider also the orthogonal directions of the given principal directions, whatever you have derived so far, and iterate this process, go on doing these things till you extract all the components. And it can be proved theoretically that if there are d-dimensional space, and these are all linear transformations, so you can get d such principal directions, you can get exact representation of information. But the point is that in this representation, what happens, slowly you will see that as you are going on, getting components and getting residuals, this residual is tending to very negligible amount, and your variance if you add more and more dimension and principal components in this way, after certain iterations, most of them would be zero, so very negligible. So you can discard them. So that is the kind of reduction it's possible. So truly speaking, if you would like to preserve the whole variance, it is in some pathological cases it is always possible that you may be possible that you have less number of dimensions, but still you have the variance intact, because you see that there are data representations. There is a vector. Let me tell you that this is a three-dimensional vector, right? And but I have represented in my data points. So these are my three-dimensional vectors. Now, if all my data points are lying in a plane, so I can define two directions only on that plane, on which if I take projections, all the components will be exactly representing the same information, will keep the same variances. So that means I require only two dimensions to represent. So these are certain understanding of this analysis. That means actually you are trying to find out the minimal subspace for representing this data point by keeping its variance intact. Now theoretically keeping intact, but you should consider there is noise, etc. So as close as possible to your representation. So sometimes the problem would be that what is the best, given the k number of dimensions, what is the best representation? That means which are the k directions which will give me the minimum loss of information, means minimum reduction of the variance of the data. I hope this should be clear to you. So if you have any questions, let me know. So this is the basic motivations and behind this analysis, and exactly this is the way we will be solving it. Right? We will be finding out those directions at each iterations where we would try to maximize the variance of the projected points on the residual vectors of the data points. So just let me go through the mathematics. So if you have any query, let me know. So you have, say, these are the representation. Say, consider X is an input feature vector of dimension D, and W is a direction of dimension D. We consider it's a unit vector that represents the direction. So projection of X along W can be represented in this form, W transpose X. And as I was mentioning that, representation or representing a vectorial space, you should have certain origin of the space in the data point representation of the vectors. So let us consider the center of the data. That means if we consider the centroid of the data, and that itself is the origin. So let us translate the origin to the center of the data point, but keeping all other axes parallel to the original axis of the dimensions, right? So principal component is a component along the vector W1 such that its variance is maximum among all possible projections. So this is a principal component definition, and I just mentioned also in my description. So this is first principal component. Similarly, second principal component, as I was mentioning, it is component along a direction W2, which is orthogonal to W1, having the maximum variance on the residuals. Once again, having maximum variance, it means that when you are projecting, actually, effectively, you are projecting the residuals. But it is synonymous. And similarly, other principal components are also defined, which means for third component, this component has to be orthogonal to both W1 and W2. And also, the variance would be maximum. Variance of the projections will be maximum. And you carry on doing this. So if there are d-dimensional space, there are maximum D principal components. So now let us consider that how the first component is extracted, and we'll see that this computation is similar for the other components also. I will take just 1 minute break. Okay, so just we are discussing that how to compute the first component, which means the direction where the projected values will have the maximum variance. So let us consider as I mentioned, X is a random variable. So that's data points. They are the observations of a random variable of a multidimensional feature vector called multidimensional random variable, and it has its mean and it has its covariance matrix. So which can be computed, which can be estimated from the data point itself. So I understand that you have already know these things because we have gone through those probabilistic inference, etc., where we have used these concepts. So the mean of projected point also, since it's a linear operation, we can show that the mean is W1 transpose N, right? So it's the same as the projected mean on the direction W. Whereas variance of Z1, this is a very interesting result, and this can be proved very easily, is W1 transpose sigma W1. So which means if I give you the covariance matrix of a data point, I can compute this variance along any directions of its projected components. So covariance matrix contains that information, and this is what it can be also shown. So, just go by the variances definitions, and from there you can prove it. So variance of the projected component is also given by this, right? So now you understand that your optimization problem can be well defined because you have this, you can compute completely, you can compute by these two statistics, mean and covariance matrix. So they're sufficient. They give you sufficient because, the total variance would be the diagonal sum of the covariance matrix. That will come later on. So to maximize variance, keeping W1 as a unit vector. So this is optimization problem. So W1 should be an unit vector, definitely. That's what we mentioned. But that's a constraint you have to consider, right? So which means that we need to find out that W transpose, so maximum is W transpose sigma W, that is the variance. And that, and also since there is a unit vector constraint, so I will put a Lagrangian multiplication factor and Lagrangian coefficients, and in that way I will consider making it an unconstrained optimization problem in this fashion. So a very standard technique. So as you can see that you have to derive, if I have to derive with respect to both W and Lagrangian coefficient L, actually, which will give you the same equations, W3 W equal to 1. So if I consider this, you can see that with respect to W, this equation, this derivation can be shown in this form. So see, all this thing is very interesting, and you may observe there is a very strong kind of similarities what you do with a single dimensional random variable or single dimensional variable for this differentiation operation, uh, when you do it for the also multidimensional variables, right? They are the matrix representations. So, that is what you get. W transpose sigma W is 2 sigma W. That is the very differentiation. And when it is W transpose W, it would be 2W. So if I consider this differentiation and if I equate it with 0, then you can see that this is the equation which needs to be satisfied for the maximization operations. There are other, second double differentiation operations also that you need to consider. That is Jacobians that you have to consider. That should be, determinant should be less than 0 there. But no, we are not putting those things here. We are simply considering this because we can show that it's a convex function and this is what is required. So this equation also gives you that the variance would be the corresponding. So it's an eigenvectors. The solution is an eigenvector. W1 is an eigenvector of covariance matrix, and since the variance itself is L, so we should consider eigenvalue, that eigenvalue of that system, that the solutions, which is maximum. So it's an eigenvector corresponding to the maximum eigenvalue. That is what the solution of W. So that gives you one principal directions and also the principal component, and its variance is also obtained from the eigenvalue itself. Now let us consider the second component, where we will see that how the residuals are treated here, just for your example, because first component and second component, they are, that difference is there. One thing is that orthogonality constraint on the vector W2 has to be put with respect to W1. So this is where your optimization problem. So you have another orthogonality constraint here. One is that it should be first, it should be an unit vector. The other one is that it should be orthogonal to W1, and which is given in this form. So you have now two Lagrange multipliers, and you need to solve them with respect to W2, and you can see that actually the equations becomes like this. So your W1 transpose sigma W2 is scalar, and W2 transpose sigma W1 is also scalar, because the dimension, if you note the dimension, so they are scalar values. So replacing this sigma W1 by L W1, what you get that this, hence L2 equal to 0. So in this way, you can show that your second Lagrange multiplier is equal to 0. So finally, once again, you get a equation which requires the solutions in the form of an eigenvector and eigenvalue. Here also you require the maximum thing. So it's the eigenvector and L1 is the variance. And in this case, naturally, it should be the second. Already the first maximum is chosen. So only the second. Now you should consider the second maximum, because L1 is the variance. So it proceeds like this. So what essentially it tells that from the covariance matrix, you find out all the eigenvalues and correspondingly all the eigenvectors. And if you sort the eigenvalues, and you know that they will be all positive or 0. So if you sort the eigenvalues, so correspondingly from in the decreasing order, you pick up the first k most eigenvalues there. So just for the k dimensional, you should choose k eigenvectors corresponding to the k most eigenvalues in that non-decreasing order of the magnitude of the eigenvalues, and that gives you the corresponding directions. So that defines the subspace. So your feature extraction would be, for any data point, you take those k components. So that k component itself will represent the data point now. So instead of d-dimensional data point, you have now k-dimensional data point. So this is what is the principal component analysis algorithm. As you see that now what you are going to do first, you have to compute the mean of the data points, because as I mentioned, it should be centered. Vectors are centered around data points. So which means translate all data points to their means, compute covariance matrix of the set, compute eigenvectors and eigenvalues in increasing order, then choose k such that the fraction of variance accounted for is more than threshold. So if k is given, then you have to choose that k. And sometimes k may not be given, and you have to find out the parameter what would be given, that because it is preserving the variance. So what is the fraction of variance it needs to preserve? Say at least say 99%, 95%. Accordingly, if you increase this fraction more, that means if it tends to 1, which means almost all the dimensions should be there. But no, if it is say 90% or 95%, so there would be certain values of k which will be less than d, and use those k components for representing the data. So one numerical example I will be showing here of this computation. So you can see here that you have three-dimensional data points. I have taken only 5 data points as a toy problem. And so you can represent the data points in the form of a data matrix. I also mentioned this term earlier. So in the data matrix, actually each column represents a data point. So this is your x, and since each data point needs to be translated to the origin means, you compute the mean of these columns, so which will come to 3.4, 4, and 2.6. That is the mean of the data point. And then you subtract this mean from each column. That's why these columns are repeated. Sorry, S bar would be, this dimension of S bar is shown only 3. There would be 5 columns. So it would be repeated. Only 3 columns are shown, but it would be repeated. There will be 5 columns. And then you subtract this mean from each column. So then you take the covariance matrix. So this is the definition of covariance matrix. You can see, actually it means that for every pair of attributes, you are computing their covariance. You are computing their covariance. So if you are considering ith and jth attribute, so ijth element of the covariance matrix will be covariance between ith attribute and jth attribute, and it's symmetric because it's the same as the jth attribute and the ith attribute. So you get a symmetric covariance matrix. So since there are 3 dimensions, you have 3 cross 3 covariance matrix, and then you compute the corresponding eigenvalue. So one thing you note that the diagonals. Now these diagonals, if you take the sum of these diagonals, that itself will give you the total variance of the data. So total variance is trace of this covariance matrix. And if I use the eigenvalues, each eigenvalue represents the variance of each component, right? And you sort them. So if you sum those eigenvalues also, that would be also equal to the total variance. So that is also another interesting thing that you should know. So all these things are mathematically can be proved very easily. So the respective eigenvectors are given this. So when you are doing dimensional reduction means you have to take dot products of each vector with respect to this eigenvectors, unit eigenvectors. You will see, actually should ignore E3. You can see also that in the third dimension variance is exactly 0 because these data points are hypothetically it has been taken and they are lying on a plane. So there is no variance in the third dimensions. Two dimensions are sufficient to represent it. So we can find that if I take the dot products with respect to every unit vectors, each row is representing a data point, not the column. Each row is representing a data point, and third dimension is redundant. So you can represent the data point using 2 dimensions. You can see also that the points which you have taken, they are lying on a plane x plus y plus z equal to 10. So just for your so if you can see that all these points are lying on a plane x plus y plus z equal to 10, right? So I have taken this things intentionally so that just to show you that theoretically, yes, it is possible to reduce dimension. Because what you are doing, you are choosing a subspace which is enough to represent this data. Suppose these are the 5 points which are represented in the 3-dimensional space. So if there is a plane and centering on the mean of this data point S bar, and these are the two orthogonal axes E1 and E2, which a plane is defined by this two orthogonal axes passing through that center point S bar. So there you can see that is sufficient. No? These two axes are sufficient to represent this data point. And that's why instead of three-dimensional space, it becomes a two-dimensional space. Right? So E3, incidentally, it should be normal because E1 and E2 should be normal to E3. So E3 gives the normal to the plane. So from the E3 itself, you know that which subspace it is. So some of the interesting properties of PCA that we discussed here, that PCA diagonalizes the data covariance matrix, which means that if you now take the covariance matrix of the principal components, then you will see that it's a diagonal matrix. Right? It would be a diagonal matrix. And then components are uncorrelated, which means that since it is diagonal matrix, it's all non-diagonal elements are 0, and which means the correlation would be 0 also. And for normalizing components with their variances, eigenvalues are there. Euclidean distance could be used for classifications. So reconstruction error from lower dimensional space, minimum among all linear transforms of the data. That is the optimal property of PCA. So that is the best representation of k dimensions. If I choose the k dimensions in this order of eigenvalues, that is the best representation of data of a k-dimensional subspace. That is what it means. There are various applications of PCA. One is data computation. As you can see that since you are reducing the number of dimensions, so naturally you require less space. So you have an alternative representation of data, and you have an orthonormal basis vectors. So, but it is data dependent orthonormal basis vectors. Now, actually, this fact is used because you see that you can consider certain classes of data with certain characteristics, like their covariance and mean. If we can estimate them, with respect to that, we can design this basis vectors. So that would be, those basis vectors will be they will give an efficient representation of the data point following that characteristics. So like one of them is that, that DCT is a very popular transformations for data computations, particularly type 2 DCT is a type of DCT. I'm not explaining the whole thing about DCT. So there are various DCTs are possible. Type 2 DCT is a special kind of DCT, and which you can find mostly they are used for computation. Now, this DCT itself, it gives a set of basis vectors, and it has been found that for the random variables, like they are applied for images or signals on one dimension, images in 2 dimension, 3 dimension. So, so there, if I consider a one-dimensional signal, now this covariance matrix, we'll find that there are eigenvectors of a 2D matrix with jk, the entries as r to the power j minus k. So this is a model of the covariance matrix. So mostly natural signals, they follow this kind of correlation. So R is a kind of correlation, right? And correlation dies down as the spatial adjacency, spatial distance increases. So that's why DCT is a very good choice of justification is there, that it is a good choice of basis vectors. Another kind of applications of dimension reduction also in color representation. So normally, you know that colored images you get represented in the red, green, blue components. That's an RGB color space. But no, you will find that they're highly correlated, because if you see the 3 images, you will see a lot of correlations among those structures. So you can perform PCAs on a class of color images, and then you can do matrix, and then you can find out the color components. Instead of RGB, you can have another linear transformation. Suppose this is one linear transformation which I'm illustrating here. Actually, it has been found by research suggested. I've given the reference of the paper. So, so that gives you a dimension, efficient representation of the dimension. So then multispectral, hyperspectral, ultraspectral remote sensing images. So color is only 3, but all these multispectral images, there are a number of bands. Like multispectral is of the order of 10, hyperspectral is of the order of hundreds, ultraspectral is of the order of thousands bands. But not all bands are informative. Only a few or a combination of them would be better informative. So PCA is a very powerful tool to get that kind of reduction and that kind of appropriate combinations. So this is one example of an hyperspectral image. We can see that in order of the eigenvalues, these PCA directions are chosen. And then if you take the components, that first component contains a lot of structural information. First few components, they contain some information. But after, if you see that after 17 or 18, it is basically dying down. So, so maybe that instead of representing in 20 dimension, or if it is 100 dimension, so it is first 20 has been shown. So 20 dimensional representation would be sufficient, or 18 dimensional representation would be sufficient. So after component 20, not much details are available. So it removes the data redundancy. There is also another applications like factor analysis, which highlights the decorrelated factors and which could be useful for classifications. Like you may consider eigenfaces for representing human faces. So this is also another interesting representation. See, you consider face recognition, and there is a database of faces. And if I consider each of them of same size, etc., then you can have the covariance matrix of the faces. I mean, represent them as a linear vector. Linearize them, then have the covariance matrix, have the perform the PCA, and then you will have those components. Now, those eigenvectors itself, they are called components of the eigenfaces, and they are linear combinations. So these are some of the examples of eigenfaces. So from the database, so first 4 eigenfaces. These are actually the eigenvectors. They are represented in this fashion in an image form. Classification of high-level and or high-level processing. So PCA can be used like dimension reductions could take place, and then you design the classifier. Like the way you consider the feature selection, similarly, PCA can be used for feature extractions using this analysis, and then you perform the classification. I think with this, let me stop today because on Friday, because tomorrow there will be your quiz test starting from 12. So please, try to join a few minutes ago and get ready. So the quiz would be, I think the time could be 12. Earlier, our time was 12:10 to 1:10 because of some have classes. So we'll keep that 12:10 to 1:10. Will it be okay? I think that will be fine. So that I will ask, tell Jayashree. So it will be 12:10 to 1:10. And so hope we will do well. If you have any questions, let me know. Okay, so if there is no questions, so let us end session here and wish you the best for tomorrow's quiz, and we will be meeting on Friday morning once again for the regular quiz.